So I didn't really change anything in the file right here. So what we are expecting for number one is that it's a general Fibonacci sequence. So you don't really need to change a lot. You just need to say okay. Yeah, let me just do it here. So basically, it's saying okay. Let me move this to the right hand side. So you have G0 equal to 0, G1 and G2 are specified, and we have the same kind of recurrence relation, gk equals to the previous two terms added up. So essentially, what you want to do here is that okay, you have like a if else condition. So if so remember k is the index, okay, for your variable. So for k equals to 0, I'm gonna return the 0, return 0, okay. L if So basically here, LIF is to somehow make sure that where you are at that line, then you don't need to go further. So if you have three ifs, then every one of the ifs will be evaluated. So that's sort of like for the efficiency purpose, you may want to do LIF instead of if. Just it accumulates. Okay, so return your input n. I think it's n. So G1 is n, and then else, well, elif k equal to 2, I'm gonna get return m, and finally, else, for any other case, I'm gonna return something using the recurrence. Okay, so basically now my index k is gonna be greater than or equal to 3, so I'm just gonna return the calling of the previous two terms, summing, is k minus 1 and k minus 2. All right, so that should be fine. And then these lines are just basically the outer grading parts just to ensure that every calculation here is correct. If they're all correct, then you will get 2 points, I think. Yeah, 2 points. Right, that's yeah, okay, it's fine. So yeah, well, you do realize here we're mainly changing two of the lines, which are the indices 1 and 2. Okay, so and then about sequence, if you're looking at the pattern of the ratio, then you just need to do it sort of like accordingly. So let's see, we have for n equal to 2 and m equal to 1, I'm gonna calculate this Lucas sequence. So yeah, well, in general, this is a really nice sequence. We can talk about why the limit is always the golden ratio, but basically, sometimes when the pattern is not that nice, you still want to get like a few numbers, like say the sequence of L2 over L1, L3 over L2, all the way up to, let's say, L11 over L10. So just do a few terms and see, okay, indeed the numbers are getting closer to some limit. Okay, so then you can conclude that's going to be a limit. So if you only compute one large index ratio, then I would say why are you convinced that it's going to be a limit? So that's something not that trivial. So the pattern is a little bit more important, because eventually in the future, if you ever play with any of your own kind of experiments, then you want to see a pattern, right? So that's something you do have to sort of look at the data and conclude. So here, what you need to let me just do it here. So what we want is that mm, let me define a function called the ratio and m. Let's say I'm gonna do steps equal to, let's say, 8. Let's say I'm just gonna do 8 steps, and now I'm gonna compute return that g function. So let me specify also m and n. So n equals to 2 and m equals to 1 by default. So I'm gonna just okay, utilize k plus 1. Wait, let me think. Okay, so probably not like this. So now we have lists, right? So what we can do here is that I start with a blank list. So ratio list. So usually this is something you would definitely want to do in practice. So start with a blank list, and then every time you append a number, and then that new list will be able to eventually plot. Okay, so today, well, probably not today, but the next time when we're dealing with lecture 9, we will be plotting things. So as long as you have like a sequence, you can plot. So I'm just gonna append this ratio, and finally I'm gonna return that list here. So return my ratio list. Yeah, let me see if okay. Of course, I need to make sure that for I in range steps, I'm gonna do I plus 1. Make sure the logic is correct, and let me also print the list, print ratio and sub n sub m. So I have the default numbers 218, right? So I'm gonna look at the what's wrong. This division by 0. Why is it okay, I see. I should probably change it to from 1 because the original term is actually a 0. Okay, so when k goes to 0, it's a 0. So I'm gonna plus 1. All right, that should be fine. So 3 1.3. Okay, so yeah, well, I may need more terms to somehow get the pattern. So if I want to do more, then I'm gonna do 2 1 uh, 13. Let's try that. Okay, that's pretty fast. Yeah, okay, and then the ratio looks to be stabilized. All right. So that gives me sort of like a pattern. Initially, the numbers are kind of oscillating, like 0.5, 3, 1.3, 1.7, 1.5, 1.6, and then indeed it's sort of like getting to this kind of like a golden ratio, 1.618, right? So that's sort of like a natural thing that you may want to systematically do in your code. Okay, so makes sense. So yeah, so whenever there's a sequence, it's really common in your future data analytical tasks. You have like a sequence or have a list of numbers, then construct a list and then just append the numbers, and then you will be able to plot. Um, but of course, I would say in terms of limits, then numerically speaking, plotting may not help you to visualize whether you are converging to a number or not. Um, because essentially, in like the limit is essentially kind of like a horizontal asymptote. So if you want to sort of ensure that you're getting close to that asymptote, it's numerically speaking, not a super easy task. So you do have to sort of get the numbers to concentrate and you look at the digits. But yeah, that's sort of what I'm kind of expecting. Okay, so you do need a number of terms to see the pattern there. All right, so that's sort of what I see the common issues for number one and part B and C. But yeah, the C part is roughly similar. So C part here, okay, it says let me zoom up a little. a little. So it says try at least 3 different pairs of values n and m. So basically, you're just saying, okay, I'm now gonna call this ratio function. Okay, I'm just gonna change n and m using like a list of pairs, and I'm gonna do a for loop. So okay, for every element in the pair, excuse me, for that any element in the list, um, that's gonna be a pair. I'm gonna utilize the ratio function, and then I'm gonna compute uh, that particular number of sequences. Okay, eventually, basically, you look at the patterns of these numbers, then essentially they indeed will converge to roughly 1.618. So that's what we are kind of trying to observe. Okay, um, so we should be comfortable by now. If not, then make sure to practice a little bit about writing loops to make it a little bit more automate. Um, right. So any questions over? So in terms of mathematics, let me quickly mention what actually is going on for this kind of like a recurrence formula. Okay, so this kind of recurrence formula. So let me not share this screen. So homework, this is homework 3, right? So let's quickly give you guys a little bit of like a context. Okay, so we have what we have. Um, f of k plus 1, excuse me, f of k, okay, f of k plus 1 equal to f of k plus f of k minus 1. And we have f0 being some number 0, f1 being some m, n, f2 being some m. Okay, so this is kind of recurrence relation is the name. So essentially, if you have something like let's say g of k plus 1 equals to a times g of k plus b times g of k minus 1. This is kind of like a generalization. So here you have the constants 1 and 1 right here. So here you have general real numbers a and b. So these are the same type of recurrence relation. Essentially, they relate to a quadratic equation. Because essentially, the thing here is that, okay, if I have this kind of so yeah, let me just write it out. So the equation is like, okay, I have a quadratic that's x squared equals to ax plus b. So there will be 2 solutions. So in general, you have x squared minus ax minus b equal to 0. So there will be 2 roots, which is x1 and 2 equal to. So basically, the quadratic formula is going to be the denominator is 2 times the constant here, and then a minus the middle constant is a plus minus the square root of this term squared minus this term times 4. So it's essentially a squared plus 4b. So in our situation, we have what we have x1, x1, x2. They are essentially, we have a, b to be 1. So it's going to be 1 plus the square root of 5. So what actually do we know about this kind of recurrence? This is a fact that's not really difficult to see. So in general, you would have the what's that term? The explicit formula for each term essentially is g of k equals to these ones. Okay, I have some constant c1 times x1 to the k plus c2 times x2 to the k. So this is a really nice fact that you can do by induction to verify. Because essentially what this says is if you look at the pattern here, so these roots, the relation between these roots are the following. So x1 plus x2 equals to a. And basically, it's the quadratic, the roots of the quadratic function. Okay, so equation. So here, this thing equals to what? X minus x1 times x minus x2. Okay, so you just multiply things out, you will be able to see the pattern, the relation that x1 plus x2 equals to A, and also x1 times x2 is negative B. So what does it mean? It means your formula here then becomes x1 plus x2 times gk minus x1, x2 times gk minus 1. And then here, this line can help you with the induction. So basically, you are saying, okay, I assume gk and gk minus 1 follow equation star. I can easily show that just doing some algebra, you are able to show that gk plus 1 also follows this equation. Right. So that's not anything difficult right here. So then what do you see? Essentially, you would see that, okay, for our scenario, we have this kind of exponential growth and exponential decay. Okay, because these two numbers, if you think about the magnitudes, one of them is the golden ratio, the other one is a negative reciprocal of the golden ratio. Uh, right. So x1, this one just blows up. Okay, and this one diminishes to 0. So essentially, you're saying, okay, my gk, roughly speaking, is xc1 times x1 to the k. So then the ratio between the neighbors is essentially going to converge to x1. Okay, so gk plus 1 is roughly speaking c1 times x1 to the k plus 1. So essentially that ratio gk plus 1 over gk is roughly just x1. That's it. And of course, for this induction argument, you need to somehow verify yourself a little bit. Okay, so this is, I would say, a relatively interesting fact um, from I think combinatorics. They analyze this, and also in number theory. But then, of course, you don't really need a lot of background knowledge in really high-end mathematics. You only need like a high school knowledge to be convinced about these facts. But yeah, so that is why you just simply change. So the initial terms. Okay, so you see in here, what are the unknowns? The unknowns are actually C1 and C2. So basically, the numbers A and B, whenever they're given, x1 and x2, they're given, right? So the rules are given. So the only thing changing there is C1 and C2. And you basically determine C1 and C2 by these two initial conditions. So F1 equal to N is just saying, okay, C1, so that's saying C1 times x1 plus C2 x2 equals to N. And this equation is another linear equation, C1 x squared, x1 squared plus C2 x2 squared equals to M. And then you'll be able to solve for C1 and C2 using a linear system equation. So the constants are uniquely identified, which is why you need two numbers, okay, to utilize for the initial condition. But then, yeah, everything is really well established. So, but then these numbers, C1 and C2, they don't really contribute to the final limit right here. Okay, so the limit here, the C1 just gonna get canceled. Okay, so that's the mathematical reasoning behind all these. But of course, if you're doing just numerically, then you just need to sort of like look at the pattern of the ratio. Okay, but the reason behind that you only need a big K, okay, to get approximate ratio is because indeed this ratio is essentially just going to converge to x1. It's indeed a fixed number. Okay. So yeah. But numerically speaking, so when there's a limit, you do need to compute like a consequent number of terms to look at the pattern. Right. So any questions so far? regarding this particular Fibonacci, generalized Fibonacci sequence. Oh, good. Okay. Um, so let me share the screen. Uh, so that's this question, and what else? I think these ones you guys have done. Oh, this one. So let me quickly mention. We have a few ways to do it. We're asking how many fib of two. Okay, so the second Fibonacci number is called when we compute Fibonacci number of five, right? So this is actually something relatively interesting. So I think I have seen a few ways to do this. So that's my original Fibonacci sequence. Okay, basically just returning one and one for zeros and first term, and then just continue computing. So one way I see that's very interesting and actually really efficient in terms of your future experiments is that basically for whatever operation that you do in your procedure, you can sort of ask it to print something really unique so that you want to see whether that line is executed or not. Then you just print that. So here, remember what are we looking at? We are looking at whether this line. Okay, we want to see. So when the fib when fib2 is called, essentially you are just seeing whether this one is fib2 or whether this one is fib2. So essentially, I'm just putting it down on the top that, okay, whether my index n minus 1 could be 2 or index n minus 2 could be 2 for the computation. That's because when you're calling a particular fib, you don't really want it to print every time fib is called, right? You only want it to be printed when fib2 is called. So that's basically saying that my input is 2 for either of these. Okay, so that's one thing that you can do. And of course, you can also do a global counter. So a global counter is sometimes helpful. Um, but in general, you do want to avoid writing too many global variables because then you will need to worry about so you need to define it, right? And then you need to if you want to get rid of that kind of line, then you need to sort of like take care of it for everywhere it appears. So that's something a little bit tricky that you may want to be careful about. But then indeed, so basically you make count as global variable, and every time you have the indices two, the index two called, then you just count add the counter, and then finally you can print the global variable because those things that are appearing in the definition of a function stays in the definition of a function. Okay, so do we have another way of dealing with this? Actually, we do. Because the third way that I wrote at the bottom is that, okay, why not I append another output that's basically telling me how many calls of fib2 is actually achieved. So that's actually another Fibonacci sequence if you think about it. So now let me. So okay, so basically I'm just gonna stop the sharing for now. I'm gonna write it on the screen to show you what I mean. So we want to know how many F2 are called, right? So here we are calculating F5. So remember F5 relies on, I'm just going to branch a tree. It's going to be relying on F4 and F3. So that's by definition. And F4 relies on F3 and 2. So this is where F2 is called, right? But then F3 also relies on F2 and 1. And then essentially I'm done because I only care about F2. So F2 should have to branch into F1 and F0, but that I don't really care. And you do realize that this term is exactly the same as this. Okay, so That means we have a third call, that's F2 and F1 right here. So essentially you are looking at how many circles are there in your system. But what I'm trying to say is the following. So when I look at F5, the number of calls of F2 is exactly the number of calls from F4 plus number of calls from F3. So it's just a sum. So in a way, you can say, okay, let me define G of okay, let me define H. So let me do H of K is um, number of F2 calls to print to calculate to compute f of K. Okay, so this is another sequence that's actually also generalized Fibonacci. Okay, because once again, Fk relies on Fk minus 1 and Fk minus 2. So if K minus 1 and K minus 2 they rely on F2 by a certain number of times, then Fk just adds up those two numbers and done. Okay, so here if Hk equals to Hk minus 1 plus Hk minus 2 because of my Fibonacci behavior of little f. All right. And then essentially, you could also just sort of reuse the code structure of my Fibonacci sequence to get two outputs. So one is my F outputs. The other one is the H output. Okay, so those are the counters. So you can do it in a systematic way. So and here we can do this because in general, if you want to say, okay, I want to know how many FIs are called, okay, for some when I compute some large index k that's greater than I. Okay, so in general, so how many FI FIs are called when Fk is computed for some k larger than I. Okay, so this is a relatively more general situation, but then you may want to think about the relationship here. So so now this is not really doing okay. I make a particular input I, and then I let me think. Yeah, so whenever my input is I, I'm in the previous treatments, I can let me think. Yeah, I can print that I is called, okay, or I can do that counter adding. Um, but one of them is so printing a certain line, okay, for many times. That makes it a little bit less tractable when you try to read those lines. Okay, so then the global counter is definitely a reasonable approach for you to exactly print how many calls are already established. That's reasonable. But here you can also do this kind of uh, Fibonacci sequence setup. Okay, so in terms of code, what do you do? So let me quickly mention. So here we're calling F2, right? So in fact, H2 is actually 0. Okay, because when I compute F2, I don't really need to call F2, right? And then H3 is calculating F3 based on F2. So remember, F3 is let me circle it right there. So where is it? Uh, so let me not change this. I'm just gonna highlight. So F3 is right here. So that will call F2 for one time. So I'm gonna define this one right here, and then for F4, if I look at F4, that's actually where? That's actually here. That's actually here. Okay, so I'm gonna highlight. Okay, so that will be calling F2 for 2 times. So in general, you definitely can think about the ways that you do these kind of computations. But here you can see that if you want to only compute H5, indeed, that's just going to be 2 plus 1, okay, which is just like the next term in the new generalized Fibonacci sequence. But in general, if you want to say, okay, how many times do I need to call F2 if I compute F of 10, right? So that's a little bit larger index. So that requires a little bit more computation. But in general, so that can lead us to the setup of our code. So let me just display it on the screen to just give you like an alternative. Okay, so make sure to think about these alternative methods that you can do the coding. It will give you a little bit more different kind of perspectives. Okay. So here my fib3. So, let me scroll down a little. Yeah, so here my fib3 gives what? So it will give me the nth Fibonacci number, and then the second component is going to be how many calls of f2, fib2. So for n equal to 0 and n equal to 1, I don't really need to call fib2, right? Only when n equal to 3, there will be some reasonable number, which is 1, that we just established. And then for fib4, it will require 2 times. And everywhere else, I'm just gonna you see, I'm just gonna reuse my Fibonacci sequence definition right here. So I'm just gonna use n minus 1 and n minus 2 term to establish my nth term. And here you see I'm just calling the 0 entry of my 2 number list. Okay. Here for the first entry, so then basically that's going to be for the index 1 entry, I'm just going to add those corresponding elements. So every time I'm just adding 0, 0 to 0. And then, so here this is 1, 2. That will give me the return value for n equal to 5, right? So basically that's the idea here. Really systematic. Okay. And in terms of the results, you see the line here is printing, okay? These two this 2 element list. It's going to be 1 0 1 0 2 0 and then 3 1 5 2 8 3 and then 13 5. So indeed, that's following our generalized Fibonacci sequence pattern. So yeah, do we have to do the global variable? Actually, no. In fact, certain numbers can be stored in terms of the function, and then you just need to somehow return it in a nice way. So this is one option. Okay. So yeah, if you care about a certain uh, parameter or variable from a function call, then you may also have the option to use it as a one more dimensional output. Okay, good. Right. Make sense? So yeah, so mm, yeah, well later I probably will share this the code to this question, but I do see that in a few number of submissions there are issues with this question, so make sure to make some changes. So right. Okay, about like the polynomial. So a polynomial is a function. Essentially, you have n all the way through a0 as the weights, okay, for your polynomial. And you remember the polynomial is a function. So what we can do here instead of writing the lambda function, we can do this. So define the polynomial function when you specify the input, okay? So that will define you a function there. But then essentially, you don't really want to return everything. You just want to return the function that you establish. So if you don't write lambda function, that's fine. You just need to define the function at the inner part and then just return the name of the function. That's still fine. Okay. So this is like a one alternative. So either way, it's going to be fine. So let me run this to just ensure that this is working properly. Okay. So that's fine, indeed. So if you want to, you write a loop, that's totally okay. You just want to be careful. But if you are doing the lambda function, then you need to do it like a one-liner, and then it's going to be a list of those monomials. Okay, each monomial you need to compute, and then you need to sum. So that's something you can sort of explore a little and get the answer. Um, Question? So I do see a few submissions are doing this approach. That's totally okay. But just make sure that your code is sort of bug free. Mm, okay, this question, yeah, this question. Let's just look at the a live coding session for lecture 8. Live coding. I think this is the one. So let me share what I have written for the manipulations and methods. So it's still our house. Let me see if let me share screen right here. Okay, so still our house, and these are old. Okay, so remember we only need the address, style, year built, number of units and number of floors to specify our house, sort of like a identifier of the house, okay, of the property. And then there are other features like the worth of the house, right? The market value. So those are something you can do as the input, but also you have the option of letting it to be like an inner variable. What I'm mentioning that the reason I'm mentioning that is that for more experienced programmers, they can write something like a web scraper so that those parameters can be updated in real time. So whenever you call that particular property, then that certain inner function or inner mechanism can return you the real time net value of the house or market value of the house. So and sometimes whether okay the house is on market or not, right? So those are certain attributes that are sort of like inner that you only know as as the programmer, okay? And then if you want to make certain attributes or methods available to public, then you will write the thing down in a program description. But all right. So then what else? So locked doors. So these are nothing special. So open window, close window, check door, check the window. So yeah, make sure that you whenever you have the like a return of a string, make it like a human readable. Okay, so that will be easier for your future computational tasks. Mm, all right. So here now we have floors. Okay, so this is something I sort of want to emphasize. So here for each floor, I'm gonna specify the parameter, well the attribute people floor with the index of the floor. So this is the basically indicating how many people are on floor 1, floor 2, floor 3, all the way up to the number of floors of your house. And then whether the lights are on up to the number of floors of your house, and whether the water is on or not up to the floor of your house. And now, how do you check the attributes, right? So that's something you want to worry about because now the number of floors is a variable. So the number of such attributes is also a variable. Okay, so you do also need a loop. Wait, yeah, check lights. So basically, I'm saying, okay, I have a floor as an input. I want to check floor 4, but if 4 is too large, then I would say, okay, that's a not legal number of floors that you inputted. Okay, otherwise I'm gonna get, so it's gonna be get attribute. So earlier it was set attribute. Okay, so make sure to play with it for setting dynamic number of attributes and getting dynamic number of attributes. It was set attribute, but here it's just get attribute. Um, that's the sort of like the only thing sort of new I want to emphasize a little. And I can make it a little bit more systematic in the sense that okay, let's try. This is the function that I defined for whether a house is unattended or not. So we have two features. We have water and lights. So if there's nobody home but the lights are on, then I would say the house is unattended, that the lights are just on, but nobody's there. But then water is a little bit different. So if let's say floor one has water running, but nobody's on floor one, and people are playing on floor two, then the property may be flooded, right? So that's if there are no people on a particular floor, but the water is still running there, then I would say the water is not attended on that floor. So there can be like different there will be four different scenarios. So water and lights that are both attended, water attended, light not, light attended, water not, and so there are sort of like different things that you may want to worry about, and to be a little bit let me see, what I want to sort of mention is that basically there's an indicator that let's say for the lights, okay, so lights is a little bit special. You want to add the number of people in your house, and then if the number of people is larger than 0 and the lights are, oh wait, if the number of people within the house is 0, but then the lights are on, then you would say, okay, my lights are unattended, right? So I need to do a loop. So these are some of the things you may want to get a little bit more creative. So I would say, okay, there's like a Boolean variable for lights unattended. So by default, I would say it's attended. Okay, but then if there's I'm gonna get the attributes, okay, for number of people on the floor, and then if the lights are on, I'm gonna switch the unattended parameter to be true. And then I just need to determine the people. Okay, so now the lights are on. If there are people, then I'm gonna switch it off. But otherwise, if there are no people, then okay, it's indeed unattended. So basically, these are the things that you want to think a little bit systematically once you realize these certain features. Okay, these certain methods. So so yeah, everything else is pretty much standard. Okay, but basically you want to get the attributes in a reasonable way, and get attributes, get number of people in each floor, and then if there's if the water is on, wait, let me see. Yeah, if the water is on and there's no people on that floor, okay, now the water is unattended, right? So basically the logic is going to be really just not really weird. Okay, it's kind of logical realization of the situation. It's just that you need to get the attributes in a nice way. Okay, so that's the only tricky thing that you need to somehow implement a little, and everything else is pretty much standard. So later, probably let's say once everyone's homework submission is well enough, and then this one will be shared. Live coding will be shared, let's say, by the end of the week, so that you can see sort of my way of thinking about this kind of more dynamic setup of the attributes and methods. So. And then, okay, I have like 3 floors, 2 floors, 1 floor units. And then, okay, so I definitely don't want to change that. All right. So basically, also make sure for whatever attribute that you write, make sure to manipulate the input data so that you test every output is working as properly as designed. So yeah. So here I have like 4 different outputs, right? 4 different check outputs. So make 4 different input instances, okay, to check that every one of the thing works. So this is very important. You may write some code and you tested, but you eventually only possibly tested part of the code. And you definitely want to test all the aspects so that every aspect is bug free. Otherwise, here the certain let's say you have if and else condition. The if part maybe is all correct, but there'll be certain bugs in the else part. And then in many situations, only if part is triggered, so there's no issue. But then possibly when the else part is triggered, then they get you something that you've felt that's out of nowhere. But so so make sure that for I do realize some of you are actually playing with like real time experiments in coding. So my recommendation here is that firstly, make copies of your working code. Okay, so do you really since many of us are kind of like beginners, so make sure that do the changes, okay, in like an incremental way. Let's say if you're comfortable with changing, let's say one or two lines, ensure that the one or two lines changed are bug free, and then you could be comfortable with that part, and then just go on with further additions, okay, further changes. So you don't really have to get into like a big leap of trying to write a new method from scratch, and then that may give you additional issues, so that you may get lost. Okay, so just make the things like a relatively incremental, and every time that you try to realize something, make sure that it's doing things as intended. Okay, so that's it's indeed like a systematic process. You will get better and better at it as long as you put hours into the coding. But yeah, those are so yeah. Well, I would say I would share the printout version, but make sure to type it out and test. Okay, to see. And indeed, I would need to admit it's not completely bug free. There will be certain small issues, but you would realize once you play with it. Uh, So that yeah, that's the question one part. This is like a reflection of lecture seven. So lecture eight, the question two. Okay, just make sure to write your less than function so that you can compare the values. Okay, the market values of house one and house two. Of course, in the ideal world, you may want to implement some like a web scraper tool so that you don't really need to input the market value yourself. Okay, but now let's just treat the market values as inputs so that you can compare. And let me also write it on my end. Just by copying and pasting and editing. So as long as make sure that you are using a right version of your code, okay, and then write your less than function. So I do need the market value here. So yeah, right. If you are using Colab, then this line is actually generated automatically, but make sure that it's bug free. So usually it's gonna be double underscore LT double underscore. You have yourself current object, and then you compare with the other. So if this market value is less than the other ones, then return true. Otherwise, return false, right? So that's the inequality true or false statement that's needs to be returned. So should be fine. LT, okay. Yeah, return true if house one less than house two. If the market value of house one is less than all right. And so once I have that, then I need to. So yeah, well, if there's a tie, probably I want to get the preference for year. Okay, so let me see. Okay, so if if they are not equal, okay. If they are equal, I want to compare else. I want to compare the year. It's gonna be what's the year built? Okay, year built. Just make it a little bit more interesting. Okay. All right. Yeah. So yeah. Yeah. So that less than method, okay, should be sufficiently straightforward. Yeah. Okay. Lake house. Yeah. I'm gonna give you guys a few minutes for the lake house, and then we're gonna put it together. Right. So yeah, so you don't really need to write a lot of lines for this particular subclass. Basically, to initialize, well, if you look at the let me see. So the inputs, okay, so the inputs here, you may not really need that many, but just depends on whether you want them to be inputs or not. Okay, so the market value was what we earlier added. So just the both status is what we wanted to change it to docked or undocked. Okay, and then the is rented is going to be true or false, right? But then everything else is inherited from house. So you just do house dot initialization so that all these old attributes are inherited. Okay, but here remember it says uh, we have only one unit. Okay, for this kind of lake house family, for this house subclass. So if I so I just put one for the number of units there. So now realize that in my new lake house, I put a 10 for in the place of the number of units. But when you print it, it's always going to be a one. Okay, so it will not be able to override that value there. Okay, so in the input because now it's just ignored. Okay, so number of units is just one. That's actually ignored. Yeah, but everything else is pretty just standard. So the inheritance, indeed, you need to call the initialization function from the superclass. But other than that, there's nothing really special. Mm, if you, you want to get rid of it. Yep, options, that's going to be a list, that's going to be the input. So this is saying that's going to be erased. That shouldn't be done. And what else? So it's division R, where you need to multiply this, you need to times, you need to multiply by the other following. It should be fine. It doesn't mean please don't. We need a graphic apart. Right. Well, you need another pair of dots, you need some things. Oh. And then you need to close it. Yes. Well, that's purple one. So that purple one is probably this one, right? Okay, so you need yeah, you need one more.
Okay.
Yeah, now it's.
Okay.
I hope that works. Okay, so the last question of today's class, let's quickly look at this queue. Okay, so earlier we were talking about stack, so let me quickly look at the nodes. So remember the stack is okay, so like this. Okay, so it's last in first out. So you have a list, but then the push is basically saying I'm gonna do this at the end of the inner list structure, but then I'm just gonna put it at the end, and then pop. I'm just gonna pop the last one. All right, so that's the coding is actually not difficult, which is what we have done in class. And then the queue is a little bit different. Okay, so it's queue is gonna be the queue is gonna be um NQ is adding a number, but now it's sort of like the rear part. Okay, so it's like the front of the sequence, the front of the list, and then the DQ is going to be removing, but it's move. Wait, okay, so NQ is the end of the list. Okay, but DQ is the front of the list. Okay, so first in first out. This is something a little bit special. Everything else is pretty much the same. So we want to construct the queue. Okay, so let's do that. Yeah, so then let's quickly also go back to the programming part. So what has it done? Okay, so for the stack class, okay, so initialize with a empty list, and then for whatever push, it's gonna add an element pending at the end, right? So when we are doing the queue, it's gonna be adding to the end. But then when we are doing the DQ, it's gonna be removing the first element. That's gonna be popping the initial part, okay, and then everything else is pretty much similar. So, oh, no, not here, but script. Okay, here. So, it's got just you guys can play with this while I'm also coding it on my own. So it's gonna be Q, but I need the object. Okay. So it's a subclass of the object. And then, of course, the much of the text, much of the syntax will be really similar to the stack family class. So initialize with the empty list as items, and then I'm gonna define NQ. Weird. To add item to queue. Okay, to the end. Last in, first out. So make sure when you're doing the DQ, okay, return some value because that's going to be the one that's getting out of your queue. And then you also need to manipulate your original list so that that thing is removed because that's the pop, right? Front. So yeah, so basically the front and rear, they're just checking elements. So indeed. So rear is the last one. Okay, good. It's empty. Uh, and to print the queue, then let's just utilize what we have done in our class. So lecture 8. I'm just gonna make sure to print the list so that it will have a similar have a particular format. Okay. So remember earlier, it's a string that I construct. So it's gonna begin with pound, separate with periods, uh, excuse me, commas, and then I'm gonna end with the at a symbol. Okay, so I'm gonna reuse the code here. So instead of this, I'm gonna do this. Okay, so and let me run this, and let me see if I can do something as we expect. S equals to okay, Q. Here, instead of doing this, I'm gonna do a sequence. Okay, so I'm just gonna do. So you can always do this kind of one-liner. Okay, yeah, right. Items. Yeah, make sure to make sure to be careful about the syntax. It's gonna be items, so all kinds of issues could occur. All right, looks good. Right. So indeed, everything you append is at the end, but everything you DQ, okay, it's gonna be from the beginning. Right. So the last question, okay, we're going to talk about the last question from on Wednesday. So there's nothing really special. You just modify the stack to get the queue. But the last question is a little bit challenge, so make sure to play with it, and then we're going to play with it also on Wednesday. This is saying what? This is saying, okay, make a stack using two queues. So here we are using the queues that we defined earlier. So what we can do is that okay, I have let's go back. I have a list. I have a data structure like this: 1, 2, 3, 4, 5. I can only add elements on the right. I can only remove the elements from the left. But now I want to utilize two queues in my stack new stack class with the help of two queues to do that kind of last in, first out operation. But this is some tricky things that you think about when you are trying to code it. So how are you going to utilize two queues to mimic the behavior of a stack? Okay, so remember stack is you add a six, right? Then the thing that you can remove is also six. Okay, so or here we have five. Then just you can only remove five. Then how are you gonna mimic this behavior using two queues right here? So that's what we're gonna talk about on Wednesday.